Patrick Neumann, Léo Perrin, and Lucas Steins.
Thank you for the introduction. So for this first non-best paper award of the week, we will be mainly focused on the cryptanalysis of block ciphers. So by block cipher, I only mean a family of permutation which is indexed by a key K. And more particularly, we will speak about substitution permutation networks. And as you all know, one of the main ways of studying the security of such a block cipher is differential cryptanalysis. So it aims at counting or estimating the number of solution X to this kind of differential equation. But graphically, what we are doing is comparing two kinds of constructions, the one where we add a constant before the block cipher and the one where we had a constant after. So just rewriting this, we are actually speaking about composition with an input translation and an output translation. But actually, if we look at symmetric cryptos, this kind of patterns appears almost everywhere. For instance, if you are doing a rotational cryptanalysis, you are doing exactly the same, except that you are using an input rotation and an output rotation. If you are doing a rotational XOR cryptanalysis, you are using both a translation and a rotation in input and in output. So our question was to ask, what happens if we try to be a little bit more general here and use a bijective linear mapping instead of this rotation? So in that case, we obtain a bijective affine mapping, bijective affine mapping in input and in output, and this is what we will talk during this talk. So actually, this kind of idea is not new. For instance, there is an even more general framework which was presented 20 years ago at FSE. But when speaking about generalization, we have to be careful because, for instance, if I told you that all attacks against block ciphers are attacks against block ciphers, well, it's true, but you don't learn anything about the attacks you already know, and you cannot find more easily new kind of attacks. And to the best of our knowledge, the framework of Wagner has not been instantiated in 20 years. So just to sum up his ideas, it's exactly the same as I explained, but instead of using bijective affine commutant, you can use any input and output mappings. So it is a very general framework. But my goal in the next minutes will be to convince you that by using bijective affine commutant, we have a large enough class to find new attacks, but a small enough class to be able to say interesting things about these attacks, and especially the link with the already known attacks, such as differential attacks. So to do so, I will present the probability 1 case and mainly focus on it because it can be explained in 10 minutes. And then I will just give a few words about the probabilistic case, which is in practice the most interesting one, but also the most difficult one to understand and to study. Okay, so our goal will be to find two mappings A and B, such that for many keys, this relation holds. And because it means that all x's are solution, we are indeed speaking of probability 1 distinguisher. So in practice, finding such an A and B is a difficult task, but we know that constructions we are using are mainly iterated constructions, sorry. So they are built using simpler round functions. And actually, in the same way as we can build a differential trail, we can build a commutative trail just by making sure that the output mapping of a round is the exact same as the input mapping of the next round. And graphically, what we are doing is we are just gluing together a commutative diagram in order to build a big one. So this means that we can do a layer by layer study, and this is what we will do for a substitution permutation network. So in order to simplify a bit the presentation, I will only focus on the case where the input and output mappings are the same. So we will really speak about commutation property. And we will look at affine mapping, which are actually the parallel application of a small affine mapping on each of the cells of our state. So you can just think about a nesbox layer, but which is affine. So speaking of SBox layer, this is the first layer we encounter in an SPN. So if you want to build an affine mapping which commutes with your S-box layer, because we used, a parallel mapping, actually we can just focus on the S-box level, and we need to find an affine commutant for our S-box. So this relation is actually a particular kind of self-affine equivalence. And affine equivalence has been solved algorithmically by at least 2 algorithms in the literatures. And these algorithms are actually effective for the usual sizes of S-boxes. So we have an answer for the S-box layer. Regarding the constant addition, we can just study it by decomposing our affine mapping into its linear part and its constant. And if we want a commutation, we want both quantities to be equal. So in practice, we want the middle term here and the middle term here to be the same. So in other words, we want the constant to be a fixed point of the linear part of the affine mapping. And finally, regarding the linear layer, we can just look at our linear layer as a block matrix with blocks of the size of our S-box. And the commutation relation between our linear layer and our affine mapping just sums up to commutation of the subblocks with the linear part of our affine mapping. And we also have a condition and a constant because A is affine and not linear. So basically, with this single slide, we have everything we need in order to build a probability 1 commutative trail. So now what we need is a candidate. So to do so, I present you the third AES-like cipher of the week. So Midori was introduced at Asia Crypt in 2015. It has 64-bit state, which is decomposed into nibbles, so into 4-bit registers. And the round function works as follows. First of all, you apply an S-box on every cell. Then you permute the cells. So it is a little bit less structured than the AES shift row, but it's the same principle. Then we have a mixed column, which uses this matrix, which is applied on every cell, on every column of the state, sorry. And finally, we have constant addition with very sparse constant, which can only be 0 or 1 on each of the nibble, and a key addition with a simple scheduling because we are using 1/2 of the key every other round. So we can now study Midori in the way I presented just before. First, by using the algorithm, for instance, the De Cagnard algorithms can state that in the case of Midori, there exists a single non-trivial affine mapping that commutes with the S-box. And I will just denote it with a star. Then we have a cell permutation, but because we are using a parallel mapping, the commutation with such a permutation is absolutely free because we are applying A everywhere. So next, we have the mixed column layer. So we had 2 conditions. First of all, the one with about the subblocks. But in the case of the matrix of Midori, the subblocks are either the null matrix or the identity matrix. And those matrices commute with any kind of linear layer. So there will be no condition on the linear part of the affine mapping. And actually, regarding the constant condition, because the Midori mixed column verifies this equation, actually, we have no condition on the constant either. So it means that the mixed column of Midori actually commute with any parallel application of affine mapping. So in particular, we will be able to use A star in parallel. And so finally, we need to study the constant addition. But so we compute the fixed point of our linear part. And sadly, the constant of Midori does not all belong to the fixed point set because 1 does not belong to this set. So in this study, we studied variance of Midori with a weak constant, and constant is weak if it belongs to this set. And for the key, it's exactly the same. We will say that a key is weak if all of its nibbles belongs to this fixed point set. So this gives us 2 to the 96 weak keys. And if we sum up what we just said, the parallel application of A star actually commutes with any layer of the Midori round functions. So it commutes with the round functions, and it actually commutes with any number of round functions, given that we are using weak keys and weak constants. So this is a very strong distinguisher because it enables to distinguish Midori with a weak key with a single pair, a single chosen pair. And it works for about 1 out of 1 billion keys. But what is actually even more interesting is the differential interpretation we can give of this distinguisher. So for instance, instead of studying our pair on our pair, which was x and a of x, we can study the difference between x and a of x and track it throughout the rounds. So we can just study the distribution of these functions. And in the case of Midori, actually, the difference between x and a of x can take only 2 to the 16 values. And because this is a linear equation, all the values are taken an equal number of times. So this means that if we are taking a random x, so a random difference pair of this form, with a probability of 2 to the minus 16, we will obtain a commutative pair. So starting from a difference, with a probability of 2 to the minus 16, we will obtain a commutative pair, which will remain the commutative pair for any number of rounds with probability 1. And if in the end we want to come back to a difference again, we will have to pay 2 to the minus 16 again. So in other words, when Midori is used with weak key and weak constant, there exist differentials with probability 2 to the minus 32. And this probability actually does not depend on the number of rounds you are iterating on. And what is actually even more stunning is that this difference activates all the S boxes at all rounds because we know that the value here, the difference cannot be 0 on any of the nibbles. So it is really unusual because we are used to studying probabilities taken over all keys and all inputs. And those probabilities are usually quite low. And we obtain them by trying, for instance, to minimize the number of active S boxes throughout the rounds. But the distinguisher I just talked about as this kind of representation, it has an extremely high probability, but the counterpart is that it only works for some keys. So finally, so we obtain this kind of results. So the differential is the horizontal line in red here, because it is independent on the number of rounds, and it has to be compared with the white-trailed arguments, which is the blue curve here. So this is not an isolated case. In our study, we also show that the Scream cipher, which was a candidate at the César competition, also has this kind of behavior. And actually, this probability 1 commutative trail has been already used to hide probability 1 differential trails in a previous paper. But the good news of our paper is that we are able to algorithmically automatically detect this kind of probability 1 commutative trail. So finally, if we look at the weak key space, we can try to increase this weak key space because the number of constraints we have is linked to the number of application of our small affine mapping A. So if we, for instance, goes to a pattern, an activation pattern with less application of A, we can expect to have an increased weak key space. So this can be done with the exact same kind of study. So we have less condition on the consent and the weak keys. We have to be careful with the cell permutation because we need a pattern which is invariant through the cell permutation. So this pattern is not invariant through the Midori shuffle cell, but it is through the AES shift rows. So we decided to study Midori, but with the shift row instead. And the price to pay is that actually the commutation with the mixed column is now probabilistic. So we have a bigger wiki space, but we have a probabilistic distinguisher. And with the independence hypothesis, we can expect to pay 2 to the -4 per round. So this gives us the green line here for our distinguisher if we expect to pay 2 to the -4 per round. And it has to be compared with the yellow curve here because we are using the AES shift row in that case. So just to sum up the talk, so what I presented to you is the probability one commutative trail case, which was almost completely done in this presentation. I just gave a few ideas about the probabilistic case. We go further in our paper, but I have to say that it is actually harder than the probability one. And we definitely think that there are many things to do in these directions, especially understanding the link between, for instance, our distinguishers with already existing work on fixed key differentials or with subspace cryptanalysis. Thank you.
Thank you for the talk. Is there any question? So can you say more about the relation of your work with subspace-based cryptanalysis? Did you try to find some relations?
So we did try to find some relation. There is one obvious, well, not too hard relation to see, is that if you are taking, for instance, the fixed point set of the affine mapping, it is actually an invariant space through an S-box or through the round function. But in the case of this distinguisher, the affine mappings that we are using actually have no fixed point because an affine mapping can have no fixed point. And so the subspace, the invariant subspace that we find is actually the empty set. So it's not very interesting as a distinguisher, but it seems to have a lot of relation with subspace cryptanalysis.
I see. Thank you. Any other question, Christina?
Yeah. Could you please go to the slide 15, the last one?
15, you said?
Yes. So yes, it's the same question as with Patrick, but with the relationship with the paper of Tim and Vincent.
So I'm not very familiar with this work. So basically, in this paper, the authors are able to compute the probability for fixed key trails, and with this kind of distinguisher, where if we use some wikis, I expect that we are able to find with this kind of strategies the same kind the same probabilities, but with a framework which is actually even more general than the one we are actually using here.
Thank you.
One question here.
Any other question?
Have the mic. I was wondering if you thought about using these techniques to design a vector cipher. Basically, let's say that is resistant against differential analysis.
For the case of probability one, well, actually our paper states that you cannot really hide this kind of backdoor with a probability one distinguisher, but with the case with for instance, if you had an affine mapping that commutes with an extremely high probability with your S-box or your round functions, but a probability which is not one. We actually have no tools today to be able to detect this kind of behavior, and it is yeah, it's a good question. I think it could lead to some backdoors.
Okay,
at least for now.
Another question?
Yes, I have a question myself.
Okay, so the last one.
I just wanted to confirm that in the quasi-differential basis, this kind of invariant or commuting affine invariant actually has a very simple representation.
Okay.
So there is a clear connection, and from it you can extract key dependency stuff.
All right.
Okay, so let's thank Jules again. So the next talk is about revisiting yo-yo tricks on AES and correcting the complexity of previous papers. It's a joint work with Sandeep Kumar Mondal, Mostafiza Rahman, Santanu Sarkar, and Avishek Adhikari. And Sandeep Kumar will give the talk.
Good morning, everyone. Myself, Sandeep Kumar Mondal, and my today's topic is revisiting yo-yo tricks on AES. And I am from University of Calcutta, Department of Pure Mathematics. So the today's outlines of today's topics are: we first give some introduction, then we described AES 128, and then we describe distinguishing game in short, and then we give some preliminary idea of yo-yo game on substitution permutation network. Then we revisit the 5-round AES and 6-round AES yo-yo attack, and find the success probability of 5-round AES and 6-round AES, and then grip the outputs result, and then conclude the papers. So at Asia Crypt 2017, Ronzal et al. Presented key independent distinguishers or 3, 4, 5, and 6 round, and the complexities are 2 to the power 25.8 and 2 to the power 122.83. Now, in this work, we revisit 5 and 6 round and find the success probability of these algorithms. So this is in AES, there are 4 functions in route function: subbyte, shift row, mix column, and at round key. And the design of AES is given here. So next, so what is distinguishing game? In distinguishing game, adversary has to distinguish between 2 oracles, oracle 0 and oracle 1. So first of all, challengers choose a random bit from 0 and 1, and then fix the oracle. And after fixing the oracle, adversary gives the plaintext to the challenger, and challenger encrypt the plaintext and give the output to the adversary. And this happens sometimes, after sometimes, and it can be chosen adaptively. So after sometimes, analyze yi, adversary give a bit b dashed and guess the oracle. If b dashed equal to b, then adversary will win. And what is the success probability? A number of actually the how many times the game is played and adversary win. So adversary win by number of times the game played is the success probability of this algorithm. So we first give some definition which are used. So first, zero difference pattern. So what is zero difference pattern? Let alpha be an n tuple, and nu alpha is the zero difference pattern of a binary tuple, and it is defined by zi equal to 1 if alpha is equal to 0 and zi equal to 0 otherwise. For example, if alpha equal to this, and here we see that alpha equal to 0 in the second and third position. So nu alpha is second and third position is 1 and other are 0. And here we also defined weight of a binary function. So weight of binary function is number of 1 present in the binary number. So here 2 1s present, so weight of nu alpha is 2. So how we generate new pair from yo-yo game? So if alpha and beta be two given pair and V be a binary vector, then rho V alpha beta is the new pair with the ith component of rho V alpha beta is alpha I if Vi equal to 1 and if beta I if Vi equal to 0. So for example, if V equal to 0 1 0 1 and alpha equal to this and beta equal to this, then rho V alpha beta is beta 0 alpha 1 beta 2 alpha 3. Here in V, second and fourth position is 1. So second and fourth position is fixed and other position is swapped. And rho v beta alpha is another pair. So from alpha beta, we can generate two new pairs, rho v alpha beta and rho v beta alpha. So simple swap is the algorithm of this swapping, and it is in quote. Actually, it is used in quote. So what is the quote? In where first texts are different, we swap the first text. So reduced round AES, here we give some reduced round definition of reduced round AES. So in one round, sub-byte mixed column and add round can sub-byte. It takes the first column to first column. So it is a super S box, and this is defined by sub-byte, compose mixed column and sub-byte, and add round key is omitted because it has no effect in Zod difference. And if we take L equal to shift row mixed column shift row, then this is the linear layer. And if we take Q equal to shift row mixed column and sub-byte, then 4 round AES can be written as SLS, 5 round SLS Q, and 6 round SLS LS, where S is the nonlinear and L is the linear layer. So what is the right pair? So a right pair is which is satisfy some condition in intermediate state. And what is wrong pair? A wrong pair is which not satisfy that conditions. So, and in case of when the random permutation in the oracle, then the all pairs are wrong pairs. And how we find the right pair? We see the output like cipher text and plain text. And if there are some conditions satisfied, then we find the right pair. So actually this is the game. For the 5 round case, if we choose to choose plain text P0 and P1, and after the operation Q, it's become A0 and A1. And if weight of nu of A0s or A1 is greater than equal to T, then it is called right pair. But we don't know this. It is either greater than equal to T or not. Here T equal to either 1 or 2 or 3. So after getting C0 and C1, which is the cipher text, and we see simple swap, we get the C-0 and C-1, and then we decrypt then, and P-0, P-1. So P-1, P-0, and P-1 satisfy these conditions. So, and if this is satisfy this condition and so on, and is satisfy every time that condition, then we take this as a right pair. And if the condition is break either, so if the weight is either 4 minus T or greater than 4 minus T, then this is a wrong pair. So in the next slide, so after sometimes how we find the wrong pair? So after sometimes this condition is not satisfied. So the algorithm for distinguishing 5 round is easy. Here X is chosen such that like this, we will choose this pair many times, and our target is there is at least one right pair is present. So here X is chosen such that at least one right pair is present. And here Y is chosen such that every wrong pair is get eliminated. So if we, in the algorithm, first of, let's say we choose 5 pair and there is at least one right pair. And if all the wrong pair, then the algorithm return this is a random permutations. So we choose Y such that a wrong pair is eliminated. So in the experiment, we see that when the black box primitive is AES, and if we choose X equal to 2 to the power 13.4, which is the expected number that a right pair is present, and if we choose Y equal to 2 to the power 11.4, which is the expected number that a wrong pair is eliminated, then the output is that detected as AES is 100 times. But when the black box primitive is random permutation, we see that the output is also AES. But that is the algorithm don't find the random permutations. So what is the discussions? So in case of when the black box primitive is AES, then here we take, let us take five pairs, and there is present one right pair, which is happen with high probability, and all the pairs are wrong pair, it is happen with less probability. So in this case, we see that first wrong pair is eliminated after 6. Here y is 7. That is the average. If wrong pair is eliminated with average 7. So in the first pair, wrong pair is eliminated after 6. But in the second case, wrong pair is eliminated in checking 9 pairs. So since 7 is the average, so some pair eliminated with less number and some with very high number. So, but this wrong pair is treated as right pair, right? Because we check up to 7. So this wrong pair is treated as right pair and the algorithm return it AES. But in that case, so it is correct, right? Since there is a right pair, so it is AES. Also in that case, this wrong pair, the second wrong pair is also treated as right pair since we check up to 7. So we cannot discard this wrong pair and it is treated as right pair and the algorithm also return is at AES. So when the black box polynomial is random permutations, then if all the wrong pairs, then all the wrong pairs, and if all the wrong pairs are eliminated before the average, then it's written as random permutation. But it not happen, right? Since 7 is the average, so some wrong pair might get more time. So here in this is the actual case when the wrong pair get to up to 9 and this wrong pair is treated as right pair and the algorithm returns it as a AES. So when the black box polynomial is random permutations, but the algorithm returns it as AES. So actually we change the y value of y 7 to 9 and this is the example. So 7 to 9 and eliminate all the wrong pair, then the algorithm return it as a random permutations. So we find actually the success probability of the algorithm in the two cases. First off, find that when the black box polynomial is AES, then the success probability is this. And when the black box polynomial is random permutations, then the success probability is this. So actually when the challenger choose AES and random permutations, they choose this randomly. So we can say that half times of choose AES and half time of random permutations. So the overall success probability of algorithm is this probability plus this probability by 2. So similar to 5-round case, in 6-round case, also the right pair satisfy these conditions. And in 6-round case, we check the condition in cipher text and in plain text also. And so on. For right pair, these conditions also happen, always happen. And for the wrong pair, after sometimes this condition will break. So this is the algorithm for 6-round and it is same as the 5-round. So the success probability for 6-round algorithm when the black box polynomial is AES this and when this is random permutation this. So, and the overall success probability is this. So in the result, if we choose value of x 2 to the power 13.4, which is the expected value that a right pair is present. And if value of y 2 to the power 11.4, then the data complexity is 2 to the power 26.8 and the success probability is 0.5, which is the from yo-yo trick with AES. And if we increase the value of y 2 to the power 15.25, then the data complexity is 2 to the power 13.65 and the success probability is 0.81. So if we try to tend the success probability to 1, then we have also increased the value of x. If we increase the value of x, there is the probability that a right pair will present. So if the value of x is 2 to the power 15.16 and value of y is 2 to the power 15.37, then the success probability is 0.99. And in 6-round case, we see that after increasing y to 2 to the power 65.76, the success probability is just 0.5004, which is almost 0.5, and the data complexity is 2 to the power 129.15, which is the greater than the exhaustive search. So we find the actually average data complexity. So actually when we eliminate all the wrong pair, then the average data complexity is computed. So if we choose y is 9 in example, then the average data complexity is calculated. So here we see that when y equal to 2 to the power 15.7 and x equal to 2 to the power 13.7, then all the wrong pairs are eliminated. And so, and in that case, the average data complexity is 2 to the power 26.82 for 5 round. And for 6 round, we see that when y equal to 2 to the power 66.13, then all the wrong pairs are eliminated. And then the average data complexity for 6 round is 2 to the power 123.82. And in conclusion, we said that when we give some algorithms, we have to find the success probability of that algorithm. And this is the references. Any questions? Thank you.
Thank you for the talk. Is there any question? Okay, I have one question. So what was wrong in the previous papers? They didn't run any experiments?
Yeah, the wrong is that they choose Y, this Y, such that one wrong pair is eliminated. The average value that a wrong pair is eliminated. That in this case, this like it is 7. But you have to eliminate all the wrong pair. Then we conclude that this is AES. Sorry, this is random permutations. So for eliminating all the wrong pair, you have to increase the Y.
Yeah, understand. And another question, why all yo-yo tricks and stuff are always against AES? They don't work against any other cipher?
I don't know.
No.
Actually, there are another cipher for AES or UUTIC 7.
Okay, thank you. Other question?
Yeah.
So first of all, answering your question on behalf of the speaker, as we already started this session, this concept, yo-yo were invented on skipjack, which is not AES, so it works there as well. And my question is as follows, because if we discuss key recovery attacks, you usually don't need to throw away all the random hypotheses, right? You're allowed to have some few random keys or wrong keys, wrong pair staying with you, and then you do the analysis afterwards. You just need to ensure that at some point of time, you're going to hit the correct key, right? You took a very strict view of the distinguisher. Have you tried to optimize and balance, saying, okay, for some of the wrong keys, the wrong pairs that you started with, you of course will get into a contradiction in the key recovery phase, and you will throw them. So maybe allowing 1 out of 100 of the keys to pass to the filtering, and then the total complexity would still be lower than what you computed.
Okay.
Have you looked into something like that?
Okay, we'll look at that.
Any other question? So thanks the speakers of the station again. Thank you.